Welcome to this lecture on transition metal organometallic chemistry from principles to applications. In the previous lecture, we were looking at the very famous 18 valence electron rules and the classification of organometallic compounds based on 18 VE rule. In that regard, what we saw that there are three classes of compounds: class 1, which does not obey the 18 valence electron rule; class 2 does not exceed 18 valence electron rule; and class 3, which obeys 18 valence electron rule. Of these three classes that we had discussed, we had looked at the molecular orbital picture of the metal interacting with the ligand and tried to explain what was the reason for various classes of compounds. In class 1, what we saw was the metal orbitals interacting with sigma 6 sigma ligand orbitals. These metal orbitals involve 5 n minus 1 d of metal, 1 s and 3 np orbital interacting with 6 ligand sigma orbital of ligand in an octahedral environment. So, what we had seen that as a result of the sigma interactions, there are 6 ligand orbital interacting with 2 d orbital, 1 s orbital, 3 p orbital, resulting in 6 bonding orbitals. These are A1G, EG, T1U, and that giving rise to two EG star antibonding orbital and there are 3 ligand d orbitals which are non bonding, they are T2G, and 1 antibonding p orbital A1G star and 3 antibonding T1U star. So, this is what we had seen in class 1 compounds, and what is the term which is of foremost interest is this difference in energy between T2G and EG star referred to as delta 0, and what it says that this T2G was non bonding and EG star weakly antibonding, which implies that both can be populated implying further that it can have about 12 to 22 electrons, and hence the class 1 type of complexes do not obey the 18 valence electron rule. With that in mind, now let us take a look at class 2 type of complexes. Here also metal has similar 5 n minus 1 d orbital, 1 n s orbital and 3 n p orbital. In this case also it interacts with 6 sigma orbitals of the ligands, giving 6 bonding orbitals and that leaves with 3 non-bonding T2G levels, which are basically d orbitals of the metal, and these 6 bonding orbital would result in 6 anti-bonding orbital, and similar to what has been encountered in the class 1 ligand, what we have over here is a similar diagram with a subtle difference. The subtle difference being that these delta 0 is much higher than the delta 0 over here. This delta 0 is much higher in energy than this, which makes this Eg star strongly antibonding. So, as a result, Eg star is unoccupied and the T2G non-bonding may be occupied. So, that is the important difference between class 1 and class 2 type of complex. So, in class 1 this octahedral delta Z value is very less. In class 2 this delta O value is very high. As a result, the total occupancy over here can be up to 6 plus orbital plus 3 9. So, it can be anywhere up to 18 electrons. Depending on T2G occupancy. So, the metals which are responsible are metals which belong to class 2 compounds are generally 4D and 5D metals, observed mainly for (4D) and 5D metals, whereas class 1 is observed mainly for 3D metals. So, it is very common for a 3D metal complex to have electrons even more than the 18 valence electron rule, and for the 4D and 5D metals which constitute class 2, they may have valence electrons which may not exceed the 18 valence electron count, and that being the case, that CFSE splitting delta Z0 for the 4D and 5D metals are inherently larger than the CFSE splitting for the 3D metals, and that is why this difference is observed. So, after looking at class 1 and class 2, we come upon a very interesting class of compounds which are class 3 types. Class 3 types are very interesting and show a slightly different type of interaction pattern. Let us take a look at class 3 type of complexes under octahedral symmetry. In this case, also the metal has 5 n minus 1 d orbitals, 1 ns and 3 np orbitals. These interact with 6 sigma orbitals of the ligand, sigma orbital of the ligand. So, as had been seen earlier, 6 of sigma orbital would interact with 2 of the d orbital, 1 of the ns orbital and 3 of the np orbital, giving 6 antibonding orbital and 6 bonding orbital. These are A1G, EG, T1U. And 6 antibonding orbital, EG star, A1G star, T1U star. Till this part, it is similar to what we had observed for the class 1 and class 2 type of complexes. But from here something more interesting happen. These compounds which are of class 2 type, they have pi orbitals, high energy pi orbitals, which can engage in bonding with 3 of the non bonding d orbitals, which does not interact with the sigma orbitals in a pi fashion with the pi orbitals. So, these high energy pi orbitals, pi type orbitals, are usually unoccupied, and as a result these non bonding d orbitals of the metal which would be filled, they would engage in pi type interaction with this unoccupied pi type interaction of the ligand. To illustrate this point, in addition to the 6 ligand orbital, let us say that there are pi type orbitals which are unoccupied in the ligand, and each of the sigma orbital is accompanied by 2 of pi type orbital, resulting in 12 pi type orbital over here. So, 12 of these 12 pi type orbital, 3 of these pi type orbital interact, remaining 3 of the d orbital which has not taken part in sigma interaction and engage in pi type bonding, giving 3 pi bonding orbital, which is T2G, and 3 pi antibonding orbital, which is T2G star. So, that leaves with 9. So, out of 12, if 3 gets involved in bonding, so 9 non bonding pi type orbital of the ligand, and these are T2U, T1G and T1U from the ligand side. So, what emerges out is a two-way interaction. First one, the black one represents ligand to metal sigma interaction, and the green one represents metal to ligand pi interaction. What is the important over here is again the difference in energy between T2G and Eg star, which is represented by this delta 0. Now, what we see that delta 0 class 3 is much greater than delta 0 class 2, which is greater than delta 0 class 1. Because of this pi engagement with the non bonding D, the delta 0 has increased substantially. As a result, Eg star is strongly antibonding and unoccupied, whereas T2G is strongly bonding and always occupied with 6 electrons. So, overall for this class 3 type of complexes, the T2G always have 6 electrons, and all this bonding this has 12 electrons, as a total all of it has 18 electrons. So, class 3 always obeys the 18 electron rule. Now, an important attribute of class 3 is the presence of synergism between ligand to metal sigma interaction and the metal to ligand pi interaction. This is a hallmark of class 3 type of complexes, which always obey 18 electron rule, and that the ligand has to have pi type orbital to interact with metal orbital. Let us take a look at some of the examples of class 3 type complexes. For example, VCl6 minus, this has 6 d electrons and 18 valence electrons. FeCN6 4 minus, FeCO4 2 minus, and so on and so forth. And all of these complexes have pi acidic ligands. So, this is a hallmark of this class 3 type of ligand. Now, let us compare across the classes of 3 different types of compounds, and what we saw is that class 3 has higher delta 0 value and they always obey 18 electron rule, and they have pi acidic ligands. For class 2, the delta Z 0 value is somewhat lesser than class 3, and they are for 4D and 5D metals. In this case, the 18 VE rule is not exceeded. And lastly, for class 1 type of compounds, this is mainly observed for 3D metals, and 18 electron rule is not followed. So, in this way I converge upon comparison of various classes of organometallic compounds and the underlying molecular orbital diagram responsible for it. I have shown the diagram and I feel that you really seen how the picture evolves from the molecular orbital interaction, and with this we come to an end of today's lecture, and we will take up some another interesting topic in the next lecture, which will look at complexes which do not obey 18 electron rule and the kind of geometries they execute. So, with that, thank you for being in this class, and I look forward to the next lecture looking at different aspects of organometallic chemistry. Thank you.